Hey, how we doing? So we're here to review, and so we'll get started right here. Hey, good to see Harley and Carson, Jeff, everybody here to do some work and to get some review done. So let's do this. Who all wants? What questions should we cover? That looks so weird. What questions should we cover? What questions should we do? What we can do is we can go to the review and let's go and grab some review stuff. The beard is hashtag exclamation beard. Are the points not working? Streamlabs, you need to be working Streamlabs. Is Streamlabs not working right now? We'll see if we can get Streamlabs working real quick. I don't know why. Sometimes it just doesn't run. I don't understand it. So this might get Streamlabs working. Let's see. Okay, Streamlabs says it's on now. And let's see. For those wondering, I had to have a little bit of oral surgery this morning. Just went to the doctor, no big deal. So if I'm talking a little bit funny, like I feel like my words, people are going to hear and be like, he sounds a little bit different tonight. What happened? So I mentioned it kind of last night, Tracy, when I was like, well, if I'm feeling up to it. But luckily everything went well. It was a local anesthetic into my gums. So doing all right. And so that's why I was like, yeah, if I'm feeling all right, we'll do it. So my hair is getting so long. So yeah, it's gum pain. So yeah, I was like, I didn't want to worry anybody. But went in at this morning, came back, and now I've got yogurt. So well, thank you everyone. We'll hop in, we'll do some review. Maybe going over those conditions. Yeah, let's do the conditions. I like my video a little bit, but I scribbled in it. So let's do the conditions again. Make sure we all know them. Hey, what's up, Andrew? Good to see everyone. Let's do the conditions to start out here. Is the sign we use the alternative sign we choose from? Yes, the one you input to the calculator, Tiffany. The sign you use is the one you input into the calculator. Correct. Oh, thank you very much, Jeff. I appreciate that. So let's do this right here. Let's make a grid of conditions. Let's review conditions to start. It's a good thing for us to review. And let's see if we can write all those conditions. Okay. So how many tests do we have? We have the one proportion z test. We have the one sample t test. We have the two sample t test, and we have the chi-squared. Now, one thing I want to mention here is that can you do a confidence interval for a one proportion? Yes or no in the chat. Can you do good to see Melissa? Can you do a confidence interval for the one proportion? Can you do a confidence interval for the one proportion? Like, can you, for categorical variables, can you do confidence intervals for them? Does anyone know, yes or no? Who knows the answer? Can you do confidence intervals for one proportion, yes or no? Like, can you make a one proportion confidence interval? You can. You can test the proportion, or you can make a confidence interval for it. Like, this is to say, like, make a confidence interval to estimate the true proportion of people who own a cat. Does that make sense? Or you could test the value to see if, like a JK, just yes. You could test. Good job right there, Luke. You could test to see if the true proportion of people who own a cat is 50%. That's why we can use confidence intervals and tests hand in hand. So when I say a one proportion z test, you can also do a one prop z interval or one proportion z interval. Can you make a t interval? Who knows? Can you make a t interval, which is an interval made for the mean? Can you make a t interval? I'm going to point to a big concept with what you're hearing through all this. Can you make a t interval? Oh, turn up the volume. Sorry about that. Let me see how close I am and let me make my volumes. So, can you make a t interval? Why are they so low? Can you make a t interval? Now it's all the way up. I don't know why I had so low. You can make a t interval. Can you do a t test? Does everyone see you can make a t interval and you can do a t test? It's virtually the same thing, just slightly different mechanics. Can you do a two sample t interval? And would that be the same sort of thing as a two sample t test? And the answer is yes to that one too. So does everyone hear that what changes, you'll always hear like interval test, but what changes is whether we say like one proportion, one sample t, two sample t. So when you say a two sample t interval, that means you're testing two means. When you say a one sample t interval, that means you're testing just one mean. When you do a one proportion z interval, that means that you're just doing the proportion for one categorical variable. So all of this good stuff right here. So everything is in place. Give me 2 seconds. I'll be right back, everybody. Magic. Can't hear me yet. Now I'm back. Awesome. So with this right here, it'll be open. The exam is open on Wednesday and Thursday until Thursday night. That is correct. So here's what I wanted to point out with what we were just learning. The conditions for a 1 proportion z interval are the same as the conditions for a 1 proportion z test. The conditions for a 1 sample t interval are the same for a 1 sample t test. The conditions for a 2 sample t test are the same as the conditions for a 2 sample t interval. So let's start doing these conditions right here, and let's make sure we have them down. I'm going to go here to layout. I'm going to change it to horizontal, and let's insert. So we need at least 4 conditions. Well, there'll be a max of 4. And so we're going to go down to here because there's our 5 rows. And then here's our 4 different types of tests. Now let's add in an extra one right here. Okay, so we got a lot going on right here. So let's do this right here. This, and can everyone see it really well, or do the lines disappear for you guys? Do you see the lines? Because in my view thing, it doesn't look like the lines are showing up. I'm going to try to make them thicker right here. Let's go. And let's go to all borders. I just made a mistake. All borders. And how do I change the thickness of the borders? Oh no. No. I can see them fine. Good. We're good. We got this. Let's center the text and let's make a grid right here. I did this by hand last time and I didn't think it looked so good. So I'm actually going to write it so you'll be able to see it better. Let's make the text a little bit bigger inside of here. And let's see what we got. There is a way to center it. And I always forget this trick. To center in the middle of these, center the text. One of these days I'll remember. Well, today is not that day. It's like one of these. Okay, let's do this. 1 proportion. And I spelled it correctly. This is a 1 proportion z interval, and let's put a note below it. Let's put right here categorical. So this is, yep, this will be posted later. You bet. Now we have here 1 sample t. This is quantitative. 2 sample t. And then let's put right here, this is quant / cat. Let's put here, I had another one I was going to do. chi-square. Can anyone tell me what the chi-squared is? What 2 variables you need for the chi-squared, which is going to be a condition down here later on? Can anyone tell me the condition later on for the chi-squared? Like, what kind of data is it? Categorical, categorical, you were right. Both variables are categorical. And then I will mention this, sampling of the mean, sampling distribution of the mean. So this one right here is a previous chapter, and it's also quantitative. I put it on here at the end. You should know it, and it's going to be slightly blocked by my head later on, but that's the sampling distribution of the sample mean. It's the very first topic that is on this test. So here we go. Can anyone tell me condition 1? I'll hit the button once someone says it. Condition 1, what is condition 1 for all of these? Condition 1, random. You know it. You know that randomness condition. Now, I'll expand upon it while I put this all in here. What does random mean? Random, great job everyone in the chat, love it. What does random mean? It means that we randomly collect the data. Nice job, Andrew. It means you went outside and you spoke to like 100 random people. Now, you can't just pick the first ones that walk up to you. You need to do it in some sort of non-biased representative way. That's what random means. 10% is next. Nice job, Sarah, right there. You know 10%. Be putting in the chat what 10% means. What does, and I'll maybe do this. I'll tell you, I'll give you a huge hint on it. What does it mean? Can anyone explain to people in words in the chat? Help them out with your words, because a lot of people look at the chat in these videos and use that to help them out, to help them study. A lot of people told me that the videos are very, very helpful. I'm never gonna remember how to center that text. So less than 10% of the population is sampled. So if UT has 30,000 students, our sample size has to be less than what? If UT has 30,000 students, which, give or take, probably 25, we need to sample less than how many? If UT has 30,000 students, less than 3,000, Tiffany, amazing work right there. That means we would need to sample less than 3,000. So that's a good way to check the 10% condition. I mean, imagine this. Honda wishes to do tests on their cars. They take a sample of 50 cars, random sample of 50 cars. Do you think Honda's random sample of 50 cars is less than 10% of the population? How would you describe that to someone? Do you think Honda's sample of 50 cars is less than 10% of the population? What would you say? I would say most definitely. Because, they make more than 500 cars a year, because for it to be is less than 10% exactly. And then remember, the 50 cars has to be less than 10% of the total population. So as long as they make at least 500 cars, then we would see that 50 is less than 10%. Like maybe they make 50,000 a year, so that'd be 1%. Nope, that'd be 0.1%, wouldn't it? Yeah, it'd be 0.1%, I believe. We can just do a double check. Why not double check the math? So we have 50 divided by, yeah, it'd be 0.1%. That was just a guess. They probably make more than 50,000, but either way, way less than 10%. I like right there. Awesome. I had a Honda Accord. It was pretty nice. And then some guy wrecked into me and my fiance. So now I have a Nissan Altima. It's also pretty nice. I like it. Has a weird variable transmission issue that has not come to bite me yet, but it will. The next condition right here is success failure. Cannot type. So success failure condition. Yep, that's what I see what you did there, Jeff. I like that. Success failure means we need to have at least 10 successes and at least 10 failures. So if you think about how they're testing a car, exactly, Andrew knows what I'm talking about. If we were to test a car to see if it's safe or not safe, which we were kind of doing in the project, we would need at least 10 cars in our sample to be safe and at least 10 not to be safe. Now, this can take a lot of forms. I'm going to draw here on a second. If you're doing the test, I might have to draw this actually. So here's the test, and here's the confidence interval. The test is NP naught, comma, NQ naught. Cannot type. And the confidence interval is NP hat, NQ hat. So that's the test. In the original one, in the sampling distribution of the sample proportion, it was NP and NQ. But now when we do a confidence interval, it's NP hat and Q hat. When we do a test, it's NP naught, NQ naught. NPQ naught. Oh my gosh, I can't even think today. NP naught, NQ naught. It's at least 10 total successes and failures. Think about this. When you do a confidence interval, you're basing it off of a sample. And when you're doing a test, you're basing it off of what you hypothesize. What is P naught in notation? You guys know I stress notation. What is P naught in notation? Can anyone tell me what P naught is in notation? Who knows what P naught is in notation? It is the something true proportion. I can post this later. I'll try to remember to post it. I can post it under the exam page. It is the something true proportion. Think about what we're doing when we do a test. What kind of we put an H word before the test. You got it, Rachel. You can't think of it. It's something you come up with in your head. So P naught is hypothesized true proportion. You are right. The hypothesized, you're totally right. And think about when you do a hypothesis, when you're doing a test, you know how you have your null hypothesis? Because the null is that, if you just write the null in a common sense, it's that P equals P naught. And so that's why we're doing the hypothesized right here. And so you used your hypothesized for the condition. And I just want to see one more thing right here. What does the null assume that P naught is equal to? The null assumes that P naught is equal to P. So aren't you basically saying that NP and NQ both need to be greater than or equal to 10? Julio, you're exactly right. You need at least 10, greater than or equal to. Don't worry if it's exactly 10. We'll never throw that. We'll never throw that trick at you. So you see this right here. I need to go back in time here and erase my highlighting. But think when you do a confidence interval now, what do you have right here? And what is this? What is that in notation? At least 10 successes and at least 10 failures. Oh, no, I won't. I will never do exactly 10. Numbers don't even exist on number lines. That's a math thing. Numbers are infinitesimally small spaces, so I'll never pick exactly 10. That'd be a mean trick. Because some people argue it could be like 5 or something. sample proportion. You're right, Rachel. And think about how we make a confidence interval. When you make a confidence interval, it's from p hat plus or minus the z star and square root p hat q hat over n square root. And this is why I don't use my handwriting. I'm actually typing it today. So if you notice right here, what's making this interval? This interval is being made from p hat and q hat. So look what you're going to use to do the testing. Does this make sense? Why, when you do the condition, you're actually going to use p hat for the confidence interval, and you'll use p naught for the hypothesis test because you'll use the hypothesized values. So just looking at mechanically what is done and what you have when you're doing a test or a confidence interval, you don't have p, and when you're doing a confidence interval, you don't have p naught. So does this all make sense here? Some people always wonder, like, why do we use this one when? Success is over sample size. Yep. And you got it right there. Great work. Let's erase. Let's go back in time here a little bit. And let's go to the next one. Now, this one is a very complex condition, which I'm going to explain here in this video because it might be the only video people watch on it. I've still got the eraser up. Maybe I click the font button. There we go. We're back to font. So the next condition right here is the nearly normal condition. The nearly normal condition. I'm going to have to scroll down here just a little bit to talk about the nearly normal on the bottom of this page. The nearly normal condition is extremely complex. The whole goal of it is that the data should look what, though? The distribution of the mean should look what? The distribution of the mean, take a guess about what the nearly normal condition states. It should look what? Normal. You got it right there. Great job, Julio and Tracy and Jeff and Ren in there. So our goal is that we have data that looks like this. Now, here's the issue, though. There's 4 ways to check this. And probably let's go to the highest level on it. The highest way to check this is the large enough n condition, which states that if we have a distribution that is normal, like if the distribution is normal, then n only needs to be 1, and then the distribution of the mean will be normal. And actually, in truth, the distribution of the mean would look exactly like it, because it's one observation, the mean of one observation, we would see the same distribution. But let's say the distribution looks a little bit skewed. If the distribution looks a little bit skewed, to make that one look normal, we'd need at least how many sample size? We'd need at least how many for this one to look normal? How many would we need for a skewed distribution to look normal? Not quite 100 yet. 25. So now, what I'm drawing here in red is the distribution of the mean. Do you notice how the one I draw in red is actually more normal? And I think you guys are thinking about the last number right here, where it looks extremely skewed. For very skewed distributions, we would need sample sizes of 100 or more sometimes. Don't worry, we won't do that on the test. But you would see here that this distribution would look normal. And I want to point out, these are the distributions of the mean. Those are the distribution of the mean. Once again, my handwriting is horrible. But you'll notice right here, I'll show you how this works. We've seen this happen a lot. Let's go do this central limit theorem applet. Let's go take a look at this right here. Okay. And let's take a look. Here we are with a skewed distribution. And skewed distribution, if I do a sample size of 5, do you guys think it'll look normal? Or what do you think? If I do a sample size of 5, I can put the website in the chat. It's a central limit theorem applet that shows how you work. I'm going to try to go for 2 hours. We'll see how long I can go. I'm already feeling a little weird. So watch the beginning of the stream. You'll understand why. No. Watch as I do this right here. The distribution down below is going to be the distribution of the mean of sample size 5. So every blue dot is the mean of 5 black dots. So you can do this repeatedly and look that this is still skewed. But if we were to increase the sample size to 25, this is now going to take 25 observations, and this is skewed, not heavily skewed. And you'll see that the new distribution down here is the mean of all of these observations here. So if you notice, does this look pretty nearly normal to you now? Does that look nearly normal? And once again, look at what I was doing over here. If you look at mine, I'm showing you the distribution in red. I'm overlaying them. And you can do the same thing with a normal. Here's the first thing I said. With a sample size of 2, do you think this distribution will be normal down here? Yes or no? With a sample size of 2, do you think the lower one will be normal? Look at the shape of the first. You're right. And so you can see we're going to take 2 observations and average them. We're going to do this repeatedly. And we're just going to do 2 observations, average them. And we'll make a distribution of the mean. And it's more normal and tighter. That's the central limit theorem right there. And that's one of the main things we like to use. You can use either a goodness of fit test. I'll mention that briefly here. You can do things. This is the 4th way, which is pretty much one of the most powerful ways to say that the distribution will be nearly normal. This is the large enough n condition. And it's part of nearly normal now. It's part of nearly normal. So it became more normal than the original normal. Well, it's still normal. So the original one was normal. So you see how this is normal up here? This is still normal. So since the first one was normal, this is still normal. But if the first one was heavily skewed, then the bottom one would still be skewed. And you can do cool things on this one. You can do right here, and you can put in, I think they had a new button. I swear I saw a new one. So you could do something like this, and then you'll see the bottom one down here is still skewed. Animated. Oh, that's connected. I thought there was a new button. I was like, I already seen the animation. So there's 3 other ways. I do not suggest them. The one I just mentioned is very important for the test. Not saying it's on there, but you know, the shape of the distribution matters if we pass. Kurtosis is skewedness. That's a measure. Wait, no, kurtosis is kind of peakedness. A statistician's going to yell at me. Kurtosis deals with the shape of the distribution like this. So the kurtosis of the distribution is kind of like peakedness. Don't worry, you don't need to know that. Don't need to know that. But that's what kurtosis is. So the other ways to check nearly normal. The other ways to check nearly normal are look at it. So if it looks something like this right here, you're good. And if it looks something like this right here, you're bad. This is not the best way, though, because it doesn't utilize large enough n. The second way to check nearly normal is to look at a normal quantile plot. If the normal quantile plot is straight, that's good. So let's draw some normal quantile plots. So normal quantile plots should follow the red line in the middle. This one right here is good, and this one right here would be bad. In the normal quantile plots, there is a red line that goes through the middle of it, and that's what the normal is. So if it follows the red line, it's good. If it doesn't, it's bad. So we'll add a green pen here so anyone watching can know. This is a good normal quantile plot. This is a bad. It's the second way to check normality, but it's mainly about the first distribution. The final and third way to check normality, which you can do, not horrible, but it only checks the parent distribution. The parent distribution, you hear me saying that, is this. We don't care about this being normal. When we test the mean, we want to test to see if this distribution down here is normal. And that almost looks normal. It might take a larger sample size of closer to 100, but if you notice, this distribution down here, the distribution of the mean, is much more normal. So we're not interested in the top one being normal, so the goodness of fit test can often trick people, because if the p-value is greater than 0.05, that is good, because the assumption is normality, and if it's less than 0.05, say greater than or equal to, then that is bad. I would not suggest this. I would go to way number 4 because we're testing the mean. So that has that condition. That's a huge condition a lot of people ask questions on. So we go to the next ones, and I kind of put them side by side for a reason right here. How do you know if you have a large enough n? Sample size. Go back and check out the part based on the samples, based on the shape of your distribution. So very similar, Sean, very similar. Based on the shape of your distribution. I took exam 2 in person. Can you talk about the online format? Yes. I'll do that right after the conditions, Katie. Remind me about that. We'll do that right after the conditions right here. Great question, Katie. But Ren, to answer your question, you look at the shape, and then if it's normal, sample size doesn't need to be greater than 1. So everything passes if it's normal. If it's skewed, sample size needs to be at least 25. If it's heavily skewed, then sample size needs to be at least 100. So the shape of the distribution dictates how large n needs to be. That's why it's called large enough n. The more skewed it is, the wider n needs to be. The more skewed it is, the wider n needs to be. Think about the condition name. The more skewed the distribution is, i.e. less normal, the more skewed it is, the wider n needs to be. Bigger, larger, exactly. It needs to be larger when it's more skewed. So going on to the next conditions right here. Where's my mouse? There we go. Do that, and mouse is back. This is also nearly normal. You have to do nearly normal for both distributions. When we test two means, we want two means to be what of each other? Or do a confidence interval for two means. What do you want them to be? Who can tell me? Type it in the chat. I'm almost there. Someone's going to beat me to it. I beat you guys. I won. So you want the two means to be independent of each other. Great job. This is a good review right here. So all that it means, if you're wondering what it means for two means to be independent of each other, that means that if you were to look at people's scores on test A and test B, you'd want to test like two different random groups of people. If you did, someone takes a test and then next week they take the same test to see how they improve, then that would be dependent. Yeah. So someone taking a test this week and then taking it again next week, their score this week would depend on their score last week. I like to use the example of people going to piano camp. Imagine you were to go to piano camp, and who here has never played piano before? Has anyone never played piano before? Like you've never, ever played piano? Anybody? Is there even one person who's never played piano? Me, Amy right there. So Amy, this is an all summer thing. You go to piano camp and you start out not even knowing where middle C is at. Don't worry, you'll learn that first day. We're like, here's middle C. Boom, right there, right next to C sharp and B, all that good stuff. So we teach you all these things. And by the end of the summer, do you think you'll have a big improvement? Do you think you'll have a pretty big improvement from the day one when you know nothing to the end of summer when maybe you can play some songs? I would say you're probably going to have a pretty decent improvement. Now, if you notice, we're going to compare Amy's before score to her after score. But is anyone here like a piano prodigy? You can pretend you are. Is anyone here like a piano prodigy? Like you've played musical instruments your whole life. You're really good at music. We're going to take Luke. We're going to say Luke is right here. So Luke's our piano prodigy. So Luke comes in with a lot of experience. Do you think how Luke is doing after the camp will depend on how Luke was doing? Jeff right there. So do you think how Luke is doing after the camp will depend on how Luke was doing before the camp? Like Luke's end of camp performance will depend on how Luke was doing before the camp. Does everyone see how these are dependent means? Like if we give Luke a rating on day 1 and we give him a rating on the last day, his rating on the last day is going to be dependent on how well he did on the first day, just like Amy earlier on. These are dependent means. We don't do that in this class. We do independent means. So you say, what would be an example with independent means? Then Luke, you're right, can't improve to perfection. Independent means would be like if we send Luke and other people to camp B, and we send Amy and other people to camp A. So then we look at the scores of people in these camps. Now we randomly assign them. Condition 1, random. We randomly pick who goes to these camps. Do you think the people in camp B will influence the scores of people in camp A? Do you think if we have camp B and camp A, do you think it's like people in camp B will do better for some reason connected to camp A? I like that right there with piano. I would say no. These are independent. So the two groups, what independent groups means is that you have a group here and you have a group here, and they're not directly influencing each other. But if someone has before and after scores like Kaplan, if you go to Kaplan to take a test, they'll test you beforehand and they'll test you after. So your after score is going to depend on your before score. So it just means that the two groups are independent of each other. That really deals with the categorical variable because that's group A and group B, or your before and after score, stuff like that. Hopefully it would improve. I agree with that right there. So now we go to the chi-squared test of independence. What do we have right here? What is the third condition? There is no real order to these, but I like to do them in order. I like to make an order for them. It's something to deal with the data. It's something data. Who knows what the third condition is for the chi-squared test independence? It means that they're both categorical. What kind of data are we looking for? It's just count data. So what does count data mean? Well, think about this. If I were to see in here, who is a senior and a, let's say, born in Tennessee, senior born, is any juniors or seniors born in Tennessee? Let's see, we're gonna do some quick math right here. Juniors or seniors born in Tennessee, you can just say me in the chat. We have juniors, seniors born in Tennessee. This is juniors, seniors, and this is freshmen, sophomores. And this is TN, we'll do some math equation right there, not TN. We got some people right there. Let's say it's like 4. And then we had people who said they are freshmen, sophomores born in TN. And then we have juniors, seniors not born in TN. And then we have freshmen, sophomores not born in TN. Does everyone see These cells right here are just what's of the data. These cells, what's inside of them is just what's of the data. As you look at the people saying me, what am I going to do to all these me's? I'm going to what them up. They're just counts. And if we add them all up, that'll be the sample size. So we see right here, these are just counts. Does that make sense why we call it count data? Because it's all just like counting the individuals that are in each group. So this is why we call it count data, because it's just a count of all the data, and it's just categorical data. It's like what meets the criteria. So that's why it's called count data right there. Sometimes I think it's important to know why we call it these conditions. The last condition right here is expected cell count. So let's type that in here, expected cell count. Sometimes my mind will blank, and I'll like, I'll either say the condition wrong, and I'm always waiting for people like, Brian doesn't know it. I'd crack up. I'd be like, yeah, I don't know the condition. I'm just kidding. So let's do a fun problem right here. You ready? What are expected cell counts? Now, people don't realize it, but they know how to do these. You know how to do expected cell counts. You already know how to do it. If you don't believe, who thinks they don't know how to do expected cell counts? How many do I have? Right under 500. Yay! I read an article somewhere that said I had 1,000. I was like, oh, they messed up. Like, maybe I should contact them and correct them. So, okay, we got people who say they don't know how to do it. You ready? Okay, Brian's going to have 200 students in his class. And unfortunately for Brian, he didn't do a good job this semester. We have here that 100 pass and 100 fail. And then we have here, this is the group that are older. No, we'll do TN, not TN. So we have TN, not TN. That stands for not TN. It's a little math symbol right there. Okay. So how many of Brian's students were born in Tennessee? How many of Brian's students were born in Tennessee? Oh, good job, Kara, right there. Keep studying hard. People are writing the formula. Great job. How many of Brian's students were born in Tennessee? You're right. How many of Brian's students passed? Does everyone see what these mean? Let's just repeat. You guys should know what this means. 100 students pass, 100 students fail. 200 students total. 100 students not born in Tennessee, 100 students born in Tennessee. Now you'll notice something here. These are kind of like counts. They're row totals and column totals. Like this is all the people who passed. So if I were to put something in here like 80, then how many not Tennessee passed? If 80 students in Tennessee passed, then how many not Tennessee passed? You're right, Tracy, you got it. It'd be 20. But I want you to not figure out, we're not going to put in the counts. We're just going to say, how many students would we expect? So think about this. I want you to think about this. Half my students are from Tennessee. Half my students passed. So think of this, a half of a half. So what percent of my students, a half of a half, think about this, what percent of my students, a half of a half, would you expect? Yeah, but we'll say expect. You guys, Jeff already knows where we're going. What amount would you expect right here? What would you expect? And Tracy gets it as a decimal, 25%. You're right, you just did the independence timesing two things together. And Julio's got the mathematics right there. Everyone's figuring it out. Good to see you, Aaron, right there. So if you notice, everyone's saying 25%. So what is 25% of 200? It's just 50. So think about this. If half my students pass and half my students are from Tennessee, then you expect half of a half to be out of the 200. If you look at the mathematics, all you're doing when you do row total times column total over grand total, you're actually taking 100 times 200, because you said half, times 100 times 200. But if you do this, this would give you a percentage, and then you're timesing it by 200. This formula right here is literally just multiplying the two probabilities together, like this, and then doing this to get the amount. Does that make sense right there? It's like, okay, I expect a half of a half, and then I'm going to multiply it by this to get the amount. But check this out. What if you do this? What if you just reduce it? If you reduce down the equation, you make that go away. Does everyone notice right here that if I reduce the equation down a little bit, let's go back in time. Here we go. So I'll reduce my equation. And now what do you notice about this? If you reduce the equation to this, all of a sudden, this is what? No, wait, I didn't remove the one thing. I erased the other one, so I'm supposed to erase that. So wait, what is this right here? Does anyone notice what formula this is? And I'll show it again. I'll do it properly this time. Let's show this right here. I'm going to remove this. And by removing that one, because those just cancel out, then it would just be this right here, and that 100 can join in with this one right here. So that 100 can be put next to this right here. And what formula is this? What formula did I just write out right there? Which is the same thing we just did. This formula is row total times column total over grand total. And you can always do this by doing the following. Here is the row total, here's the column total, and here's the grand total. This will go into this cell right here. Does that make sense? Does that make sense, Rachel? How I can use this formula right here, which is actually just our multiplication rule. Interestingly enough, this is the multiplication rule. It's the expected value for the cell. You're right. This is expected cell counts. And let's make sure we put a note in here, greater than or equal to 5. At least 5. Except the 25% part. No, that's when you just do the 25% part, which we wouldn't ask. Don't worry, I was trying to show some theory on why it is this. The 25% part is because I expect 1/2 of a half. So because since it's 1/2 of a half, that is 25%. And what is 25% of 200? 50 right there. So you can use the 25% and you can do like expect half of a half. Like watch this. What if Brian said, we'll go way back here in time. We got to go way back now. Oh, that's good. That's good. Now you know the theory a little bit. It helps when you understand the theory because then you can like figure it out for yourself. You can be like, wait a minute, I can figure this out. What if all of a sudden this changes to something more reasonable? I want you to think about this. 10% of Brian's students, oh gosh, that's horrible. We don't want to do that. 10% of Brian's students fail, and 90% of them pass. So with 10% of Brian's students failing and 90% passing, what percent of his Tennessee students would you expect to pass? What percent of Brian's Tennessee students would you expect to pass? Go ahead and try to write the formula and then double check it with just understanding it. So 90% of Brian's students pass. Sorry, I misspoke. 90% of Brian's students pass, and 50% are from Tennessee. Then tell me the expected for this cell. How much do you expect in that cell? Who knows how to get that one? How many do you expect in that cell right there? Nice job, Abby, right there. Abby wrote the equation. She's 100% right. And Brianna figured it out. You guys are right. Great work in the chat right there, helping each other out. And I've got the mic arm. I might unpack it. Just waiting for it to decontaminate. It'd be 90. And guess what? Then this one's 90. And then, this one's 10. These are all the expecteds right here. And a cool trick you can do is the expecteds have to add up to the totals. So once you know one, you're good. I do want to mention one more thing right here. This is a 2x2. What are the degrees of freedom on this test? This is a 2x2. What are the degrees of freedom on this test? With a 2x2, what are the degrees of freedom? Abby, you're right. It's 1. You know it. 2x2, turn into a 1x1. You just do reduce by 1. And then 1 times 1 is the degrees of freedom. You guys got it. So last but not least, we have the sampling distribution of the sample mean right here. And this one's fairly easy. This one just has large enough n. So nice and easy right here. Do I have a bigger font? Good. So this one is just large enough. And we covered that earlier. Make sure to rewind the video. You'll see me here on this one right here. I do want to put this here, though. Want to add one more note for people watching is that so does the Z distribution have degrees of freedom? Does the Z distribution have degrees of freedom? What are the only ones with degrees of freedom? What are the only two with degrees of freedom? The Z will not. The Z will not. So this one right here is nope. There are no degrees of freedom for this. We don't do it. So there's no degrees of freedom, right? T and chi-squared, you're totally right. You guys are awesome in the chat. And then the one sample T, if you remember how the one sample, when I say one sample, and this one's just a formula. And this one is, I need to write that nicer. And make that R look like an R. There we go. Can someone put in the chat for anyone watching the video? I can write it, but I want you guys to write what this formula actually is. And I guess I might put a little bumper right here. So, oh, it's Streamlabs is working. Awesome. Sometimes I think it doesn't start at the start. It's rows minus 1 times columns minus 1 is what we were just doing. So to do a practice on this one, if you had a matrix here that was this, how many degrees of freedom does this have? How many degrees? Nice job, Tracy. How many degrees of freedom does this have? Anyone know really quick? You should be able to boop, figure it out. It's a you got it, Sean. You know it. You know those really quick. If you notice, you can just delete out. A lot of times what I say is delete one row, delete one column, and then you can see there are 3 degrees of freedom. There's the 3 degrees of freedom right there. So you guys got it. It's a 4 by 2. So when you reduce it down, it's a 3 by 1, and 3 times 1 has 3 degrees of freedom. So just a good practice right there on the degrees of freedom. Next, we could do this. If your sample size for this problem right here was 681, what would be your degrees of freedom if your sample size was 681? Oh, thank you, Ren. I appreciate that. Oh, no. Well, we've got a bunch of people in here who watch a ton of streams. So what does the degrees of freedom do for us? It's kind of your residual error. It's like the amount of variation. That's more of a high. Don't worry, that's a really great question. But the degrees of freedom are used to tell you the right distribution. I guess I should keep it 201. The degrees of freedom are used to let you know what t or what chi-squared distribution you are using. They can be used in other senses to tell you what f distribution you are using. But yeah, it's like for the residuals, which we're not going to get into that. we're gonna study for our final and not 320 or upper level classes finals. But it'll tell you what t or chi-squared you're using for our class. Does that make sense? Really great questions. I appreciate it. Like, I want you guys to be like, so what does that mean? What is kurtosis? That was a really great question. There's a really great Wikipedia article on kurtosis, and it's like, some people think it means peakedness, but it doesn't mean that. I'm like, well, whatever. I was taught peakedness. I still think, when I look at the graphics, I'm like, it looks like peakedness to me. So I know I should get my stats better. Well, that's got that. What should we do now? We just went over a really great review of the things. When you can you define everything on the formula sheet? Yeah, let's do the formula sheet. Let's do that. Okay, give me just a moment right here. I sent it out as an announcement, so I'm gonna have to go get the formula sheet. Let's go grab the formula sheet. Let's do everything on it and make sure people know that. So just a moment. Oh, logged out. How is everyone doing tonight? How is everyone doing? Good, bad, in between? There you go. I almost have the formula sheet up. See what people are saying on how they're doing. You've been playing Breath of the Wild? That is awesome. I started the master question. It was really hard. I think I know this is a question for exam 2. I thought the formula sheet was included on the exam. Or we supposed to print it off? You can print it off, or you can write it down if you can't print it off. And then Katie was asking a question earlier about, like, what is the exam like? It's basically multiple choice, true, falses. Go take a break. It's basically multiple choices, true, falses, and I don't think it's too bad. One of the best things I can tell you to do is, if you've done all the quizzes, do all the homeworks. And I know I'm like trying to promote my own videos and being like, hey, go watch these videos. Let me put them in the chat here again. So here, I'll exit out of this one. But the playlist I made that goes over these sample problems, I think is a very, very good playlist. So I would suggest watching it. I'll put it in the chat here in a second. And then we're going to go over the formula sheet. But just knowing how to work problems and knowing the conditions, probably some of the best advice I can give you. So this playlist, which is going to be the right playlist for once. I keep sending the wrong playlist because I called it like the same thing as another playlist. So this playlist right here, let's make sure we got it. Right playlist. All right, so we got the playlist. Let's drop it in the chat. Don't leave this video now. Hang out on this video more. But this is the playlist right here I've been suggesting to people. It goes through each type of problem with a very specific example. And so I suggest watching these. I know they have the ads on them. Remember, we are taking, I think we've almost made, can I look at that right now? We've almost made like $4. We're almost there. We almost have enough for one pizza, everybody. And it's right there, Luke. There's the playlist. It's in this video now, but we almost have enough for one pizza. We're getting there. We're getting the pizza money. So, but I'm really excited about that. So let's look at the announcements. And once again, I won't put ads on like these videos because I can technically put ads on these videos, but nope, not doing that. Okay, here we go. It's a PDF. Can I draw on PDFs? Let's see. 2 seconds here. Okay, so let me just screenshot this. How's it going to look on a screenshot? We'll find out. We will find out. Here's the official Stat201 formula sheet in a PDF. Okay, so new. There it is. Look at that. Brilliant. Okay. Let's see how everyone's doing here. Please post the document. Yes. I'll make sure I save it. So I'll make sure I'll save it for you, Rachel, right there. Let's talk about money for everyone. Yep, I think I can do it, Aaron. I think we'll do that probably on like Tuesday. That's tomorrow, isn't it? Yeah, let's plan to do it tomorrow. So I'll put out the word tomorrow and it'll be recorded. So let's plan to do that tomorrow. Does that sound good, Aaron? Sorry, I had surgery this morning. So awesome. That's why I was a little bit afraid. I didn't know how I'd be after it, but I seem to be doing okay. Yay. Seem to be doing okay. That's what we like. Okay, let's go ahead right here. Does it? The one on the previous exams looked different. This one's just better organized, but this is the one we've sent out. This is the one that Terry made. So if you don't have this, Rachel, email me and I'll send it to you. You can use this one right here. You can print it out. It's a little bit better organized, kind of very easy to see what goes with what. So, this was sent out via an announcement. Did anyone get this via my announcement? I sent this in an announcement. Yeah, I'm doing okay. My gum had to get fixed, so yay. They like needle. Yeah. You got it? Okay, awesome. I'm doing okay though. That's why last night I was like, I think I'll do this tonight. And then I was like, okay, I'm good enough to do it. So let's take a look right here. What do we have right here? Yeah, the one the practice exam is different. We made it look nicer. We made it look easier to read. If you don't have it, email me. I might even post it to the Stat201 site. So look after this. I might put it just on the Stat201 webpage. That way people can easily get to it. Okay, let's take a look right here and let's see what's going on. Here is the pretty much the earliest chapter on the test, and this is the sampling distribution of the sample mean. So when we do the sampling distribution of the sample mean, this right here says that we expect the mean of the sample mean to equal to the mean. Now, that's a really confusing concept. Like, I could lecture on this concept I've highlighted here for probably like 5-10 minutes, and people might even still say, like, wait, I don't get it. Let me put it in context. I'll like try to explain it really quickly. If I tell you that the average guy is 5'10", and I talk to 50 guys, what would you expect the mean of those 50 guys' heights to be? So if I were to talk to, you got it, Rachel. So remember, a guy is 5'10" on average. So when I told you a guy is 5'10" on average, what did I just tell you? When I told you a guy was 5'10" on average, I told you mu. I told you that guys are 5'10" on average. But then, what mean do you expect for the sample mean? That's the second part of it. The mean you expect for a sample mean of 50 guys or 25 guys would still be 5'10", because you expect the mean to be the mean for the sample mean of a certain amount of observations. Now, it doesn't matter what n is. That'll matter later on for the next equation. But imagine this. If you were to say, when Brian plays a basketball game, he usually scores 8 points. Maybe that's good. That's probably not pretty good. I don't know. I'm playing against high schoolers. I might have a shot. I'd probably still lose. But if Brian were to play 50 basketball games, how many points would you expect him to score on average? If Brian were to play, yeah, not like that, Luke. If Brian were to play 50 basketball games, how many points would you expect him to score on average? Brian scores 8 points on average. What would you expect him to score on average in 50 games? Just like on it, my average is 8 points. What would you expect? 8 points per game. You're right. The 8 points per game that I score is right here. I told you the mean of my score is 8. But then if we look at what mean do you expect in a sample mean of observations, you would still expect 8, because it's like, well, Brian scores 8 on average. But the second one right here, we'd expect 400 total. But remember, 400 divided by 50, Katie, would be what? 400 divided by 50, let's check it. 400 divided by 50 is 8. So you are correct. You'd expect me to score 400 points, but you'd expect a mean, you would expect the sample mean of it to be 8. Does that make sense, Katie? You expect 400 points, which is you would expect 8 points on average per game. And the first thing I told you, it's very subtle, but I said Brian scores 8 points per game on average. what would you expect his mean score to be? That's the second part over. What would you expect his mean score to be over 50 games? Does everyone understand the small difference right here? Brian eats 3 cheeseburgers when he goes to McDonald's on average. Brian makes 100 visits to McDonald's. How many cheeseburgers do you expect him to eat on average? Now, what's the answer to it? Brian eats 3 cheeseburgers at McDonald's. Oh, we get wait 30. I'd love 30 cheeseburgers right now. I can't even eat cheeseburgers. I gotta eat yogurt. So you're right. It'd be 3. It'd be 3 right there. You know what I miss? I miss cookout. I miss so many things. I'm going massive quarantine. So right here, let's look at the next one right here. This is the standard deviation. Now, the mean controls the center of the distribution. Ooh, space pen. The standard deviation controls the spread of it. And what does the spread do as n gets larger? The spread of the distribution gets what as n gets larger? So n is sample size right here, and sigma is standard deviation. So the standard deviation of y bar is going to get tighter. Sean is right. Because just think about this. Just imagine, go way back in time right here. Just imagine that this is getting bigger, and as that gets bigger and bigger and bigger and bigger, then it's going to make sigma smaller and smaller and smaller and smaller. And that's one of the parts of the central limit theorem that states, yep, so as n gets bigger, the standard deviation gets smaller. This right here is the sample size. Like Brian goes 100 visits to McDonald's. This right here is the variation, the standard deviation in how many cheeseburgers Brian eats. This would control the spread, like Brian generally eats between either 0 and 5 cheeseburgers, or Brian eats between 2 and 4 cheeseburgers. Now, these are the same, like just comparing, but which of these would have a bigger spread? 0 to 5 cheeseburgers, and I know you could debate it. Don't worry, statistician's not here to debate us. But which of these looks like it has a bigger spread? 0 to 5 or 2 to 4? 0 to 5, you're right. And y bar is the sample mean. So this is the y bar means the standard deviation for the sample mean. Now the sample mean has with it a sample size. So y bar is the sample mean, and it's the standard deviation of the sample mean. What this is going to do is this is going to allow us to draw a distribution, which did I already remove it? Oh no, I made it go away. Let me bring it back up. Central limit theorem applet. Okay. So what this allows us to do right here, the whole point of this, is to take the original distribution up here. And one of my favorite things to do is ask you guys this question. Let's use these 2 formulas right here and practice them. So I'm going to show you the 2 formulas, and I want to ask you the answers to the question while you look at this distribution. The mean for this distribution is 16. What do you think the mean for the distribution of the sample mean will be? The mean for the top distribution was 16. That's the original mean. What will the mean for the bottom distribution be? You're right. It'll still be 16. Do you see how it's still 16? Now, the original standard deviation was 5, and we're doing now a sample size of 25. It stays the same. You're right. So since our standard deviation is 5 and we have a sample size of 25, then what will the new standard deviation be? Let's look at the formula again here. So remember, our original standard deviation was 25, was 5, and our sample size was 25. Yep, 5 divided by square root of 25 is 5 over 5, which is 1. And we can confirm that this works, and you'll notice this is tighter. It's going to take the sample of 25, and then we look at what happens as we do this. So if I click the wrong button, and you see it is 1. So you actually just figured out something theoretically via the central limit theorem. So this formula right here, how this was acquired, this number was sigma over square root of n. This number right here was mu y bar equals mu. And this one is sigma over square root of n right here. This is the new standard deviation. This one right here, the one I'm currently highlighting, is found via this formula right here. This formula right here finds the answer for this one right here. So we can make our own custom distribution. Let's make our own custom distribution right here, and Brian's just going to do this really crazy like, and I wish I could do a whole number. I can't though. And then let's use 25 again. What will be the mean for this bottom distribution? What will be the mean for this bottom distribution? Remember, mu y bar equals mu. So what will be the mean for the bottom distribution? You are right. And then how would you, because the sample size is 25, it's here also, how would you find the new standard deviation? the new standard deviation will be what over square root of what? So we have to take the original standard deviation divided by the square root of what? And then see if you can do it. Yes, 7.42 over square root of 25. And so that will solve out to exactly 1.45. So there we go right there. That is it. You got it. That has got it. Excellent, excellent work. That is that part of the formula sheet. Okay. And then the last but not least thing, this is a z-score. A z-score is merely the sample mean we observe minus the hypothesized amount, and then we have the standard deviation right here. And did we put that down lower too? Did we put that there? I disagree with where that's put. Wait. And then we put it right here. I don't know about putting that right there. I wouldn't put the mu naught over it. So that's, well, tomato, tomato. It is a z-test then. I don't know if this has been asked, but any idea of the day of the projects? I'm hoping in the next 4 to 5 days. The graders are really busy. I told them to be really nice. So if you did really well on it, expect to do really well. And you can always use the Canvas has like a grade estimator thing. So you can use the grade estimator. Good question there, Luke. I'm going to check in on them because some of them are grading them and some of them aren't. But good question there. Next, we see right here, let's zoom in a little bit on it so we can see exactly what Brian's talking about. We have confidence intervals right here. This right here is what? I need to see it in the chat. You could. Depends on, it's very close, Rachel, but I think all of us are going to be very nice with grades. I mean, we can't just give away A's, but, you know, we're going towards the nicer this semester. Sample proportion, this is X over N. This is like saying, out of our 100 customers, 70 are from Tennessee. So what would it be? You got Luke right there. X over N. X would be 70. N would be 100. And this would be 0.7. So this is a number between 0 and 1. This right here is the thing that gives you your what level for the interval. It's like your 68, 95, 99.7. So when you change what the Z is, you're changing the what level of the interval. Think what it's called. The confidence, you're right. So this is the direct level of the confidence right here. It works the same for the T down here. The T is in the same position, and the T controls the confidence down there, just like the other intervals. So that part of the interval controls the confidence, and we will give you things like that. It can only be up to 2 points. Extra credit is only 2 points. So if you're at like a 91, you get to a 92. So it's only up to 2 points. It can't get you from like an 85 to an A. It can't do stuff like that. It's only for like getting you to the next grade level, which is good. But and it can't get you to like an 83 to an 89. So if you're a low B, it can't help you out. We would give the Z-score, Brianna, right there. You got it. It's my way of like doing nicer rounding, and I'm really nice with it this semester. I'm really nice. The standard error right here, which we've written as a separate part, let's make this very clear. That would go right there. I can't make that more clear. That is that thing right there. And this is P hat times Q hat over N. Ow. That was fun. P hat over Q hat over N square root. And what do we have for P hat? What is Q hat? That's my question. What is Q hat? What is Q hat? What is Q hat? People should know this pretty instantaneously. What is Q hat? Like in my previous problem, P hat was 0.7, so what is Q hat? We call it the P hat Q hat game. 1 minus P hat is Q hat. So it's 0.3. 0.3 would be from my previous problem. Just 1 minus P hat. Q hat and P hat are complements of each other. You got it. Nice stuff. And now we get down to hypothesis testing. This is going to get us a z-score here, but I want to point something out. Are these two the same thing? Like, are these two things right here the same? Is that z the same thing as this z? Like, are they the same thing? No, don't do that. No, they're not the same thing. People do that. Don't worry. Don't worry. Don't worry. I say this and I make such big marks on it because every semester it's a common question. Because when you see it, you're like, oh, this z right here. But why does that z have a star? That z has a star because you get to pick it. So this z right here, that z right there is the z that controls the confidence level. But it's not the same thing. You pick it. You say you want to make a 68, so it'd be something close to 1. You say you want to make a 95, it'd be 2, or 1.96. You say you want to make a 99.7, it'd be 3. And so this z right here is a what? is a something whatized. This z, when you do a test, is a something whatized. Look at the top part and just think about what we're solving right here. We're just taking a what, and then we're doing what to that what. And that's what this z is. It's just a difference standardized. You got it. We're standardizing a difference. Does everyone see here? We're just finding how far these things are apart, and then we're standardizing it. That's all we're doing. It's a standardized distance. That's what a test statistic is, the z being created right here. So with this in mind right here, let's look at what the p hat is. The p hat is the sample proportion. The p right here, I'm not happy. The p naught right here, that's a p naught. The p naught right there is the hypothesized. So it's what you observe in the sample. We've been going on since 8. Check it out. The p naught right there, which I will be changing to the formula sheets. Sorry about that. There's a p naught on that. The p naught right there is the hypothesized. And the standard deviation is going to now use p naught and q naught. So the p naught and the q naught are going to be used over here because we're doing the test. So we see right here that this formula right here is just really like our observed minus our expected over the standardizing factor, which is going to be very similar to something later on. Now, it's not observed minus expected squared. Don't do that. Don't do that. It's this formula right here, and you do get this sheet, and I will correct it to p naught. Very sorry about that. That should be p naught. We'll get that corrected for you guys right here. And then we go on to the next one right here. What is y bar? I want to see what y bar is in the chat. Who knows y bar? It's pretty long, like 50. I don't want to. It's pretty long. But we are going to, if the exam grades are like really low, we're going to obviously do something, and it is averaged together. Sample mean. It is pretty much like that, Tracy. It's what you observe in the sample minus what you expect according to the hypothesized amount. So it's very similar to observed minus expected squared over expected, which we'll see later on down here. And, but it's not the same. Just like this one right here, this formula right here might as well be observed minus expected over the standardizing factor. And that's just how we do tests, is we just take a difference and we standardize it. So everyone's saying that this y bar is the sample mean. You're right. So if you look at this right here, this is your sample mean. Like Brian averaged 2.5 cheeseburgers on his visits to McDonald's. We see right here the T, which controls our confidence level. Remember, it was in the same position as the thing before. So that's going to control your confidence level. And then last but not least, we see the standard error. The standard error is very similar to the previous formula. Remember, this just goes right in here. So the standard error goes right there. And it's S over square root of n. Now, I did have a saying. I don't use it as much anymore. But S and T, sigma, Z. So if you notice this, when you have S, you'll use T. Does everyone see here we have S? Where'd my cursor go? We have S, and we're using T. And then up here, we have sigma, and we're using Z. So sigma goes with Z, and S goes with T. There's more specifics on that, like with William Gossett, who made the T distribution and why he made it in the degrees of freedom. But all this good stuff right here. But this is the formula and the standard deviation. This is standard deviation of a sample. Please slow me down if you don't know what one of these is. This is like the standard deviation of a sample, and this is the sample size right here. The formula is the standard error of the mean. Sample mean, excuse me. Standard error of sample mean. The degrees of freedom for this test are n minus 1. That tells you the T you're using. Next, we go on to this one right here. This is going to solve for a T. Are these two things the same thing right here? Yes or no? I need to see it in the chat. Are those two things the same thing right there? Are those two things the exact same thing? I think I heard someone outside say the answer. Like, what was that? They're not. They're not, though. They're not. They are not. They're not the same thing. They're not the same thing. Because this T right up here is the T you get to pick related to your confidence level. And this T down here is the T you solve for when you standardize the difference. So this right here is a test where we take the sample mean, we subtract the hypothesized mean, and then we divide by the standard error. And all we're doing is taking a difference and standardizing it. And that difference standardized will turn into this T statistic right here. Does that make more sense to people right there? That is the difference standardized, which will be the T statistic. So good stuff. This is like a big mega review right now. This is complicated stuff. If you're following along 100%, you really know what's going on with the class. So, because this is pretty high level right now, I will admit, because I'm trying to give every concept that we've gone through. There's another mistake in the formula sheet. Oh my gosh. It's a good thing we're looking at it now. So y bar, you're only 40%. We'll get to 100%. Y bar 1 minus y bar 2 plus or minus t with degrees of freedom. Let me put this into a parentheses right here. There we go. And so this is a confidence interval right here. Should have my mom say hey. So, hey mom, I'm broadcasting online. You want to say hey to my students real quick? You're live now. You want to just say hey to them real loud?
Hey students.
There you go. So yeah, there's my mom right there. I'll let you go, mom. Bye. So yep, FaceTime. So good stuff right there. Everyone said, I'll tell her everyone said hey. She can watch the video later and see it. That's pretty cool right there. Thank you guys very much. Yeah, so this right here is sample mean 1 minus sample mean 2. What will this find right here? What will this find right here? What does that find? The white random moment. You're totally right. We'll do more randos in a second. What does that find right here? What does that find right there? That finds the what between the two whats. Because think, what are we making a confidence roll for? What's that find? That is literally the what. It's over there somewhere. What are we making a confidence roll for? You're right, difference between two means. Boom, right there. That's what that is. The difference between the two means. Just look at what you have. You mean 1, mean 2, and you subtract them, you find their difference. And then we have right here, all of this. All of this is the what for the interval. I haven't talked about that much lately. All of this is the what for the interval. Everything I've highlighted there after the plus or minus is the what for the interval. Everything I've highlighted right there is the what. Everything we've highlighted right there is the what. Margin of error, right, Tracy? Excellent work. That is the margin of error. And the t with the degrees of freedom tells us the confidence level. And then the standard error, this is this. So that whole thing is right there. You don't, once again, this is not solved right here. You don't solve this. It is that right there. That is that. I can't point. I'm a mirrored image and I can't tell where I'm going. So that is that thing right there. The way this is written, we have it right now. It's like this right here is this. That is what's there. And so that is the standard error, which is what you standardize by. I'll just quickly review what these things are. I need to update and change this formula sheet. Here is the standard deviation of sample size 1, the standard deviation of sample size 2, the sample size of the sample size of sample 1, and the sample size of sample 2. This is like Brian wants to see how many cheeseburgers he eats at Cookout versus McDonald's. So Brian makes 10 visits to Cookout and 20 visits to McDonald's. The standard deviation of the Cookout visits was 1 cheeseburger. This is the standard deviation, not how many cheeseburgers I eat. It's the amount of variation in the cheeseburgers I eat. And the standard deviation for McDonald's was 1.5 cheeseburgers. I didn't eat 1.5 cheeseburgers. The variation in the amount of cheeseburgers I ate was 1.5. So what do I mean by that? It's like a variation of 1 cheeseburger might look something like this, where my cheeseburger eating might go from 1 to about 7. Oh my gosh, that's insanity. You can't see it's behind me. 1 to 7. I should have did 0 to 6. But Wendy's, yeah, Wendy's is really good. Man, Wendy's dollar menu, that was a guilty pleasure of mine when I was on archaeology. Like you go to the dollar menu and spend like $5 and you'd have food for the next day. It's so bad. So that's got this formula right here. And now the next, when I answer in a percent and when in nominal, the nominal percents are used for proportion, Tracy. Percent is used for proportion. Yeah, Wendy's fries are awesome. Man, I want some Wendy's now. Wendy's and McDonald's. I'm just gonna get a whole buffet. So generally the mean can be any number. The mean can be it could be very small numbers because you could be doing, you You guys got me so hungry talking about these Whoppers and stuff like this. Burger King Whopper. Oh, what about the Burger King bacon cheddar ranch burger? That was the best of all time. So bacon cheddar tender crisp ranch or whatever. The guy from Hootie and the Blowfish used to sing about it because it was that good. The confidence roll down here. You can forget about the 0. We don't need it. It's 0. Minusing 0 does nothing. And then you have right here the difference between the two means. And then you have the standardizing factor, which is just this. So that is that from right there. Oh, I'll try the Impossible Whopper. So I'm so sorry, guys. Yeah, nah, that'd be so bad right there. That would be that I would not want to watch it. I was like gripping the chair. I was like, the needles in the gums was not fun. So for the views, one of these days I might play video games on here and see if people actually view it. I might do like a live stream. I've thought about putting an emulator on here. Would you guys check it out? If I made a live stream where I played and tried to beat Mario in under, I can beat the first Mario in under 10. I can do that right now. I want to beat it in under 7. World record's like 456, or maybe they got to 455.7. They're shaving off frames on it, doing frame rolls and everything. But I might try to beat Mario in under 7 minutes, which I think I could do. So if people would watch that, if people would watch me play Mario, I'd actually play it on here. You would watch that, Andrew? Maybe I'll do a live stream. Let's play with Brian. Yeah, exactly. Like maybe I'll do a Mario stream. So maybe I'll do that. I'll install an emulator on here, and I've got a USB controller. So maybe I'll try to, if you guys would like that, maybe we'll do that this weekend or something, or maybe who knows. But I'll be like, okay, let's beat Mario 1 under 7 minutes. You know what we could do? We could record the times and see like how well I do. So we could actually use the real speedrunner thing. So check it out. Breath of the Wild. I don't think I have the capabilities to hook in my Switch. I do have a Switch, but I don't think I can hook it in. My other game systems are too far away to grab right now. Breath of the Wild is amazing, though. Breath of the Wild is such a beautiful game. The last but not least formula we have is the chi-squared, which is the distribution we're using. So you find the chi-squared, and then you do observed minus expected. These are, the observed is what you view in the cell. It's the actual amount in the cell. The expected is found via the formula, row total times column total over grand total. And so this is how you find each of these expecteds right here. And this is the sample size. The degrees of freedom formula is right here. It's just rows minus 1 times columns minus 1, and that's got it right there. I know switches are awesome. They're all sold out. But I think that's got it. Rows minus 1 is just how many rows there are in the matrix, and columns minus 1 is how many columns there are. And then expected is rows times columns. So you write the formula. This one right here is when you go here and you have like 100, 100, and then maybe you have 80 and you have 120 and you have 200. So you do it the following way. You do row total times column total over grand total. Hopefully everyone can see that. It's barely visible. So that would be 80 times 100 over 200. So that's 800. Oh, I should be able to do it a better way. My brain is just so slow tonight. So that's 40%. Oh, 2 seconds. Be right back. Take a small break right here. Be right back. You guys solve this problem and I'll be right back. Now you can hear me. Great job, everybody. Might do just a few more off on here, and I'll probably hop off so that way don't hurt myself too much. But what last few things we want to talk about? I might do a stream tomorrow night. We'll see, because I'm doing the other one. Maybe I'll do it tomorrow midday. Usually freer during the days. What do you guys think? What other things? I think we covered a good bit tonight. What other questions are there? Does anyone have any other major questions? I'm back. How hard should we study this last chapter? It's actually one of my favorite ones. This last chapter is probably for two sample means like what would it ask? Good question right here. So two sample means would ask something like if we were to test, let's say, who eats more cheeseburgers, Florida or Tennessee? We'll probably do more tomorrow, and we'll go over beta tomorrow because I'll probably go off here in just a moment to give myself a rest. If we were to do who eats more cheeseburgers, Florida or Tennessee, that would be two means. So we're seeing the amount of cheeseburgers that Florida students eat and the amount of cheeseburgers that Tennessee students eat. So when we look at this right here, we need to talk about the mean for Florida students and the mean for Tennessee students. Does that make sense right here? So when we write out this, the null always has the what sign. The null always has the what sign. I would say pretty similar, pretty similar. So we go here, mu1. And I didn't really give a directionality on it, but if you notice, and I have a really good, when did we do it recently? We did all the different conditions. We did it recently, we did all the conditions, but and all the nulls. But one thing I want to promote, because I might be going off here in just a second. I've been telling people as I've been saying that I had surgery this morning. It was a lot of fun, especially during the current world situation. It's like, so what I'm suggesting to everybody is, and when I probably head off here in just a moment, is, oh wait, I started the practice exam, and for number 3, I know in your video you talked about which one went first and between the two. Oh, good question there. I think I know what your question is, Abby. In jump output, they always put, and let's show some jump output on this. When they do two means in jump output, they always put, maybe you think of some last one. Yeah, definitely. And I will be streaming tomorrow, so I'll do some streams tomorrow too. So expect more. I'm sorry, I've been on here not too long tonight. I usually stream for longer, but I will stream tomorrow. So tell everybody Brian is going to stream tomorrow. So when we go right here and we go to analyze fit y by x, and then when we go to tip amount and we do it by payment method, we will get here a 2-sample t-test. And let's make this nice and big. Oh, thank you, Ren. I appreciate it, guys and gals. So we go right here, and here it's going to be a 2-sample t-test. So here is the 2-sample t-test right here. Now, if you notice right here, we should know all of this output. And make sure, remember, we do this in a lot of things. The reason, now, when you look at this right here, do you see how it's cash minus card? That's how we know the difference is. Now, which of these paid more, cash or card? Which of these paid more? Who knows the answer for which of these paid more, cash or card? Thank you, Tion. I really appreciate it. You guys are awesome. You guys give me a bunch of energy. Which of these paid more, cash or card? You are correct. Because if you look at this, it's big number minus small number, which would equal a positive number. Because the difference is positive, it is cash. Now, I've gone over this a little bit here, but I want to make sure you guys know this. We've brought up this question. But watch this. I'll show you a trick. If you have this output, you know the null and the alternative. Does everyone see this? Well, now it looks horrible. Does everybody see this right here? All you have to do to write the null and the alternative is do the following. The alternative, or the null, is the mean for cash minus the mean for card is equal to what? The null is that the mean for cash minus the mean for card is equal to, you could literally almost write it out right there as the subscript. What would the difference be equal to according to the null? The null is that the mean for cash minus the mean for card is equal to 0. There is no difference. Think about what you could do. you could literally just bring this over to the side. And what are you saying about the two values? If you were to bring this over to the other side by way of just algebra, then you'd be saying the mean for cash is what to the mean of card. Since they have no difference and you just bring it over, what would they do? They'd be what to each other? So if you just brought it to the side, you'd be saying the mean for cash is what to the mean of card, since they have no difference. According to the null, that's what we're thinking. Not really opposite, but think if you were just like take your and bring this over to the other side with algebra, you got it, Jayla, right there. They're equal because they have no difference. When you're saying that you're hypothesizing the difference is zero, you're saying that you hypothesize there is no difference, and mathematically you could just bring this over to the other side, and then you would get that the difference is equal to zero, or that they're equal to each other. There is no difference, they're equal to each other. That's what the null states. And the alternative right here would be any of the following. So we got mu cash minus mu card. And it could be something like not equals 2. This would be the right p-value for this test right here. But once again, we need to look at the question itself. So the question will tell us what way the alternative goes. And right now, since I'm using the does not equals, it'd be this right here, and this, and this. I tell you guys what, how about tomorrow midday? I think I can do a stream midday. So today we only went like an hour, but tomorrow midday, let's look at all the jump output and let's go through each test and jump and talk through every bit of jump output. How does that sound? Like tomorrow, midday, what do you think? Maybe 2-ish? Maybe around 2, we'll look at all jump output. When the p-value is low, you reject the null. Definitely. We reject that there is no difference. We have evidence of a difference between these right here. So this was a short stream. We covered some really great topics today. 2 would be great. Let's plan for 2 tomorrow. So if you're here right now watching this, 2 sounds great. We're going to go through all the jump output, come with tons of questions, ask them, and this is really good review. Make sure to have your notebook out and be taking notes. But Jared and everybody, so great to have you. Check your points again. And I'm going to head off here in literally like 1 minute or so. But I appreciate everyone so much. I will be streaming again tomorrow. Thank you so much. I'm on some ibuprofen, so nothing too crazy. But I appreciate it. And you guys are doing excellent. Let's see if points are working real quick. And then we'll head off. But you guys asked for it. We, of course, got to hit the button again. Random button. The exam is open all day Wednesday and all day Thursday. The exam is open all day Wednesday and all day Thursday. All day Wednesday and all day Thursday. Thank you, Ren. I appreciate it right there. Thank you, Jayla. Thank you so much, everybody. Like, you guys are so awesome. Thank you, Carly. I appreciate it. It's just like a little bit sore. You might have. I'm not closing my mouth completely when I talk. I made that mistake earlier in the stream, and then I was like, ow. It's like shot of pain through my mouth. Oh, thank you, Joel. There you go. Everyone, you guys are awesome. Katie and Abby, I really appreciate you guys. We'll end with a rainbow. End with a rainbow. You guys got it. Keep doing those homeworks. Keep doing those quizzes. And I will see everybody tomorrow at 2. I'll send out some reminders. There's gold at the end of the rainbow. So see everybody tomorrow at 2. See you then. And bring some questions. Talk to you later. Bye, bye.